Hi, welcome everybody. We've got about 15 people so far, a few people here in the room, a few more online. So I'm Mark Mondol, and I've been doing e-beam lithography at MIT for about 30 years now. And I started doing that in Hank Smith's lab in Nano Structures Laboratory over in building 39. Well, actually in building 38, where we set up an e-beam lithography tool based on spare parts from IBM with Juan Ferrera's help when he was an undergraduate here, before he became a graduate student. So with that, I guess I'm going to continue. There we go. Motivation. So why are we doing e-beam when everybody in industry is making these terribly tiny structures and everything at a great rate? And the answer is they're using steppers, and steppers require mass. Masks are expensive, and steppers are expensive. So DUV steppers could do features down to tens of nanometers. But nowadays, for the advanced semiconductor chips like microprocessors, people use EUV at 13.5 nanometers. And if you look at the picture on the left of the screen there, you can see there are two people standing in front of this tool. You can also, if you look more carefully, you'll see there are at least two people standing on top of the tool. It's that big. And 150 million is probably actually a low ball estimate of a current state-of-the-art EUV stepper. And it doesn't even use refractive optics. It does everything by bouncing these X-rays off of very fine and smooth mirrors. So this is a great way for making a huge amount of the exact same chip over and over again, really, really cheaply. And that's not really what we're trying to do in research. So in research, what traditionally has been used, well, not traditionally, but what is being used right now are laser writers, typically like the Heidelberg MLA150, of which MIT.nano has two, or the SUSE mask aligner, which most fabs, I should say research labs, have one or more of, or possibly an add-on pattern generator to an SEM. And when you look at the various advantages and disadvantages of these things, there's price to think about, in resolution. Resolution is really the driver for most of these things, although sometimes it's throughput when you're doing research. But most often it's resolution. So with a mask aligner, you can get down below a micron, but you still have to make the mask, and you have a fixed pattern that you can make. You have no flexibility without making a new mask. So the solution is to have dedicated e-beam lithography tools. So back in around 2012, we installed the Eleonix F125, which is a 125 keV tool. And then just last year, we installed the HS50. Before that, we had Wraith 150, which is a converted SEM column. And before that, we had the IBM tool I was talking about earlier. So the characteristics of these tools are very similar between the F125 and HS50. The differences really are, most notably, is voltage. We'll get into why that's good later on. The field size, basically, again, because of voltage, you get a much bigger field size with the HS50 than the 125. And the HS50, which is installed in MIT.nano rather than building 24, is specifically designed to have a lot of beam current down the column so that in some situations anyway, you can improve your throughput. However, e-beam lithography tools are not copying machines. I mean, if you get a mask right and you expose it in the resolution range that's reasonable for it, it will pretty much copy the pattern that you designed and had made. E-beam lithography has a lot more variables and things that you have to worry about. So for background, they're not cheap. They're sort of $750,000 to $3, $4, maybe even $5 million. And the resolution typically gets down to around 5 nanometers or so. And then one other thing I wanted to say before I moved on is I am only going to be talking about Gaussian beam vector scan tools that get used in research. In addition to that, there are tools that have variable apertures that shoot shapes onto your substrate. And just recently now, probably in the last 4 years or so, in industry, there are multi-beam mask writers that will have 1,000 beams or many, many more. And these are used for using an electron beam to write a mask that will later be used in a stepper. But we're not talking about that. We're talking about tools like this. Well, can I get rid of this or not? Oh, So at the top, we've got the gun. And the gun is sitting at the acceleration voltage. Right after that, you have some alignment coils, and then a condenser lens, which pulls as many of the electrons that are coming down the column as possible and focuses them into a beam that sits on top of a blanking aperture. The blanking aperture is there so that you can turn off the beam when you need to. Then there's typically on the tools we have, lens 2 and lens 3, which work together in a kind of zoom lens arrangement. And that allows you to vary the size of the beam here on top of the beam limiting variable aperture. And that means when the beam is very wide, you get little part of the beam through and you get low current. If the beam is very focused, you get most of the beam through and you get lots of current. Then we get down here to this octopole stigmation column, which coils, which I have misspelled, my apologies. And what that does is it tries to make the beam nice and round rather than ellipsoidal. And then we get down to the final lens, and actually the beam deflection, again, we'll get to that, a little bit of that later, is happening inside the lens via 2 plates that, 4 plates that electrostatically deflect the beam left and right and up and down. And then we hit the sample in the stage, and now my graphic is in the way. And then you have an XY stage with laser interferometer. So, at the top is the gun, and the gun on these kind of tools is typically a thermal field emitter. That means you've got a single crystal of tungsten that's got a coating of zirconium oxide on it. It's heated up to about 1800 Kelvin or so, which allows electrons to get pulled off the zirconium oxide and come down the column. After that, we have this suppressor that limits the diameter of the beam, basically the area of the tip that's getting electrons pulled off of it. And then the electrons are accelerated through the hole in the anode, which is at ground, and then the electrons travel ballistically down through the column. The gun, as we said before, is a single crystal tungsten with zirconium oxide source on it, and it's got a flat of about a micron across that is controlled by the suppressor to some extent. Guns do die, and you can see the lifetime here of like 9 to 24 months, but sometimes they fail unexpectedly. The column itself needs to be a good vacuum so that we don't get the electrons hitting air molecules, gas molecules as it travels down through the column. Most importantly, we have very good vacuum up at the gun, and the vacuum gets lower until we're down at the exposure chamber where the electrons actually hit the substrate. There's a lot of control and feedback that goes on here. We want to make sure that the substrate is at the correct focus, which we do with the laser height sensor. We have the stage drive, which is controlled by the laser interferometer, which makes sure that the stage drives to each new field correctly, but also feeds back any errors in the stage position to the beam deflection to make sure we accurately place our pixels and our shapes. We need to keep the column at a very constant temperature so that we don't get drift in the column. And we need to change the focus and stig as we move through the fields and make sure the lenses are correctly focusing the beam. This illustration shows the beam blanker, which cuts off the beam as we move in between shape and shape so that we don't expose patterns in between shapes. But then within each shape, we need to raster the beam through the pixels that compose each individual shape. This illustration doesn't quite accurately reflect the column that we are using or that many lithography systems use, because this deflection of the pixels within a field is usually done with deflection plates or magnetic coils that are actually inside the final lens itself. Next, we have pattern formation, where we break down the pattern that we have designed previously and want to expose into its shapes. With some sort of pattern that you might want to write. In this case, I'm showing a kind of photonic waveguide pattern, and it's huge. It's 5 millimeters by, oh, let me see this, sorry. to 7 millimeters wide. Now, we're not imaging with electron beam. We're scanning the features. So we need to decompose this. Sorry. Into single, I missed the slide. There we go. We need to decompose this big pattern into many little fields that can be written with our ability to deflect the beam. And that tool I'm illustrating here, the F125 at 125 kV, the maximum we can deflect the beam is 250 microns away from the center. That's about 300 volts. It's required in the column. And we need to do this at a fairly high speed because we want to write quickly. So here I showed the pattern decomposed into 500 micron fields. And then if we zoom in on one of these fields, sorry to whomever's listening. And we look at one field, we see what's going to get written within one field. And in fact, within that field, the pattern gets broken down into smaller shapes. So if we zoom in some more, we can see this curve in the waveguide getting decomposed into many small rectangles and triangles and trapezoids. We zoom in further, we can see that there's a plethora of little pieces that are used to make up the pattern so that it has good fidelity. So once we get down to the primitive level, we have to think about how we're going to fill up these shapes. So there are different ways of doing it. And the way that most commonly used is this flyback scheme, where it's kind of like old TVs used to be. You're going to write a line, you're going to move back, you're going to write another line. Sometimes you have the ability to fill the thing with a spiral pattern, either spiraling inwards or spiraling out. And this can be very useful for getting a nice smooth edge. You can see at these corners, at these edges here, sorry. At these edges here, you might get a little bit more noise. And if you fill it smoothly like this, you'll have less. Or you can do these other schemes, which you can implement whether or not your tool has different fill schemes by pre-preparing your pattern, is to write edges around with small beam current and then fill in the middle with a much larger beam current and still maintain nice edge roughness. So the beam we use to expose with, I did my best with graphics, but not very well. And this is meant to be a 2 nanometer diameter beam. And that beam is not really this columnar-like thing that I'm showing up here. It's a Gaussian beam. So the full width at half max is nominally 2 nanometers, but you have to remember that these tails that are coming out here that are going to overlap, and due to other effects like proximity effect, that means we don't have the kind of beautiful, sharp on versus off that you might think you have. So here's an example of a primitive shape filled with 10 nanometer pixels and a beam that's nominally 10 nanometers wide at the full width half max. And the way it does this in this example is it's going to probably scan along the long axis of each one of these rectangles. And it's going to come back here, scan, come back here, scan, like that. Sorry. Next. So that scanning is controlled by the pattern generator, and that controls the beam deflection, and it's going to have something like 16 to 20 bits. But it doesn't actually scan over the whole field at one time because we're trying to get as many bits as possible to define the grid that we're writing upon. So it subdivides the main field into subfields. And in the HS50, those are 10 micron subfields, and the F125, those are 20 micron subfields. So it's going to go to one subfield and it's going to write the information in that subfield, and then it's going to move to another subfield. What I'm trying to get across here is we have these sort of nested DAC situation, so that it's not just 20 bits we have to define shapes, but it's sort of the main ADC and the subfield ADC. So this is what the field might look like. You get this 500 micron field that gets divided up into little subfields. And if you divide this 500 micron main field, you can, by 50,000, which is the smallest number that you can divide it by, you get 10 nanometer pixels. We can also divide it by 500,000 or even 1 million steps and get much smaller pixels. So how do we move from one field to the other field and have everything match up in between the fields? And that's because we have a stage that's controlled or feedback is given by a laser interferometer that measures very precisely and accurately down to about 0.6 nanometers the position of the mirrors that are on the stage that hold your wafer, your piece. So that means we know really, really accurately where we are in terms of the mirrors. Now, if you stick a cold wafer on a hot stage, you're going to get thermal expansion and things won't work so well. Conceivably, if your wafer wasn't held down well, you might have problems. There are other things that might affect it. So we know where the mirrors are, but not necessarily the thing that we're writing on. Actually, the main thing that gives you an indeterminacy of where you're writing is charging in the wafer that deflects the beam. So how do we get the deflection to be so precise? Because we want this deflection to sort of be good to at least 1 part in 10,000. And the answer is we close the loop with the laser interferometer. And the way that's done is we put a mark here in the middle with no beam deflection whatsoever. We scan across it in X and Y, and then we find the center position of each thing. So we find the center position in Y, center position in X, from our secondary electron detector. And then we tell the stage to move. In this case, I'm saying 225 nanometers, 225 microns in X and 225 microns in Y. And we also tell the beam to move that far. So we move the stage, move the stage and we move the beam. And if everything was perfectly calibrated to each other, our circle would be right back here in the middle, but it won't be because there's drift with time. And instead it shows up over here. We measure the distance in between these two things, and then we recalibrate the deflection of the beam deflectors that tell the beam where it's going to land. So this is sort of repeating what I already said. We actually calibrate the field not just at the corners, but throughout the field, so that we can use a rough quadratic equation to recalibrate the deflection points. So here's what happens if you don't have a field-corrected beam. You get a lot of fields that might be 500 microns across, or maybe they're 520 microns across, or some other number. They're not always rotated so that the axes of the beam deflection align with the XY axis of the stage of the mechanical deflection. And in addition, there could be pin cushion or a trapezoid keystone, other kind of effects. After we calibrate the beam, and then when that happens, you have two features that are supposed to match right in this at the edges of the field, and they don't. After we do calibration, everything lines up so that our beam is moving along the same axis as the XY interferometer is, and features that cross field boundaries will butt up against each other perfectly, or as best we can. So here are examples of field distortions, and of course, you don't just get one distortion at a time, you get a convolution of more than one kind of distortion at a time. So this was the work of a PhD student back in the early 90s who very, very carefully calibrated fields and did a nice plot here of what the field, 100 micron field in a Wraith 150 looked like. And it's showing you vectors, it's showing you vectors here that are 500 times bigger or magnified with respect to the XY axis, showing where the displacement is. This is on a tool that was based on an SEM column. It isn't going to have great fidelity or perfect fidelity. It's only a 100 micron field. The Elionics tools should look better than this, even at 500 or 1000 micron fields. But there will be placement errors that are dependent on the lens itself. So how do you get stitching and placement errors? Well, like I said before, if the substrate's cold and your stage is hot, or the opposite, if an old style magnetic deflection tool that you're trying to drive the beam faster than it can really get to where it's supposed to be, the fields are bigger than you want to write a lot of stuff fast, so you decide you're going to write big fields, you're going to have bigger Placement errors, charging of the substrates, the one that's most commonly you'll come across as a user. In addition to bad coordinate transformation, if you don't really understand what you're doing when you do sample preparation, it's easy to get a coordinate transformation that leads to errors. And then if you're writing very small things or things that need to be connected across fields over long periods of time, some of these drift terms that aren't a problem when you're writing for half an hour will become a problem when you're writing for 8 hours. And of course, sometimes the equipment just screws up and you find out about it later. So what are the practicalities here? This is the part that Juan is going to do. And Juan and I have worked together on and off for 30 years, and he's really good at proximity effect correction.
So first, a little about myself. I started working on the first tool that MIT got from IBM Research. They gave us a pile of spare parts, and we put together and brought up an e-beam writing machine. So this was in the early 90s. And then we started doing some e-beam lithography with that. So yes, I've been doing e-beam lithography on and off since the 90s. Okay, let me get started here. So you've set up your e-beam writer. Everything has been aligned. Your lenses are very well aligned to each other. You have a beam spot of say 2 nanometers, and your deflection is also been very carefully set up. So you can expect that if you write a pattern, you should get sort of 2 nanometers or maybe 5 nanometers sort of resolution. And then you go to expose this pattern, which I have here as a cartoon. So let's say that these squares here, these 2 squares are maybe a micron, and then this line is 1/10 of a micron. So you would imagine if an e-beam writer is the same as a printer, you program it to write this, and that's what you're going to get. But once you do the exposure and you do the development, then what you get is this. So you can see that it's not nearly what you wanted. So you have the 10th micron line has pretty much disappeared. All you have is a little knob here. The line has disappeared from here, and it's just the whole thing has turned into a block here, and the line has disappeared from here. And you can also see that there is some rounding of the corners. And so what happened? What happened is that when you use an e-beam to write something, you have to deal with electron scattering. So when your electron beam hits the solid substrate and it goes to the resist, but then you can see that it starts scattering. This is a Monte Carlo simulation of the scattering process. And you can see there are 2 kinds of scatter. So this is an amplified view of what's going on here. This is the resist, and this here is the substrate. You can see that when the electron beam hits the resist, it starts being scattered by electrons, by the electrons in the solid that compose the atoms in the solid. And then it also generates secondary electrons. It'll generate gamma rays, and it'll generate X-rays, and all those sources of energy will actually start exposing your resist. In addition, there are some backscatter electrons, which you can see some of the trajectories here, like this one here, has where you remember the Rutherford famous experiment where if an electron or a particle hits the nucleus of an atom, it would scatter at large angles. So this is what's happening when an electron hits a nucleus, then it'll be scattered at a large angle. And it only takes a few collisions like that to get the electron to reverse its path and to enter the resist again. So this is what's called backscattering. And you can see the backscatter range can be as large as 30 microns. And this depends on the acceleration voltage. And forward scattering also depends on the acceleration voltage. The larger you make the acceleration voltage or the energy of the electron that's impinging, the less forward scatter you get. But the trade-off is that your backscattering will increase. So 30 microns would be for a larger energy. And here you can see from the top how the electrons are being backscattered back into the resist, and they're creating exposure outside of the area that you want. So people ran into this problem pretty early on, and they also devised a solution. So here's a paper from 1975 by Philip Chang, where he recognized that there is a point spread function, so that if the electron beam hits at this point, there's going to be energy deposited at a separate point, and the energy that's being deposited at the point P just depends on the radius of the distance, the radial distance between Q and P. So they recognize that you can build a point spread function, which is this function here, and all you have to do is convolve it, and then that'll tell you how much energy is being dissipated. So let's try with a one-dimensional example. You have this pattern, which is P of X, and then convolve it with the point spread function. And there are two components to the point spread function in this example. So you have the forward scattering, which is this slightly sharper, higher energy. And then you have the backscatter, which is much more distributed and at a lower level. But if you integrate it, this can actually be a rather large part of your exposure. So once you do the convolution, you will end up with energy deposition that looks like the red dotted line. You can see there's also the backscatter component, you can see here. And also the forward scattering means that the slope here is not an impulse or a step like you initially designed. So you have blurred edges due to forward scattering, and then you have a background and exposure due to the backscattering. Usually when you have a convolution problem, you can invert it, but in this case, energy can only be deposited, it can't be taken away. So once you deposit energy in these areas where you don't want it, you can't take it away. So the only thing that you can do is change the dose, for example, of this line should get larger dose, and then hopefully that will equalize the threshold with respect to these red dots, which is where you want the pattern to be resolved. So this is this process that we do to invert the scattering is called proximity effect correction, and it involves two steps. The first step is to calculate the point spread function, which is done with a Monte Carlo simulation, and that's what the plots that I showed you before are done with a Monte Carlo simulator. Once you know the point spread function, you can calculate the convolution of this PSF, and then calculate to do an inversion, which is like I said, it's not an easy problem because of the background being always present. But there is people have been developing software to correct for the proximity effect for a pretty long time. So to calculate the PSF here at MIT.nano, we have this program from Genesis called Tracer. And this allows you to very quickly define your resist stack and your substrate and obtain a point spread function. So here's an example. And you have a three-dimensional view of the energy deposition. And there's also a two-dimensional view, which are slices at different heights. So this is where the beam impinges, and you can see how the energy is being deposited. Let me point out that the radial scale here, this is the radius in microns, and down here is logarithmic, and also the exposure here is logarithmic. But you can see how there's a backscatter. This, by the way, is gallium arsenide wafer with 500 nanometers of PMMA exposed at 50 kilo electron volts. And you can see the beam being forward scattered, and you can see this green area is where the backscattering is taking place. Similarly here, this line here, the red line is the energy deposition at the top of the resist film. You can see that it's fairly sharp. It actually follows the radius of the incident beam. You can see an intermediate regime here where the exposure goes down gradually. You don't have the forward scattering and the back scattering. There's a certain amount of mixing between the two in this region. And at the resist bottom, which is a purple, you can see that there has been a lot more forward scattering, and the back scattering stays pretty much the same for all layers in the resist. And this shows the difference in acceleration voltage. So if you use a 50 kilo electron beam to expose 500 nanometers of PMMA, you see that here you have a fairly large amount of forward scatter, but a smaller amount of back scatter compared to 100 kilo electron volts, where the situation sort of reverses. You have less forward scatter, but you have larger back scatter range. And this is showing the same plot, but as a two-dimensional energy density. You can see the forward scatter the purple is the 50 kilo electron volt, so it's it would be this. It's a little less sharper in the forward scatter regime, but it's you have less back scattering. And similarly, 100 kilo electron volts, you have a sharper forward scattering part, but more the forward scattering part is sharper, but you get more back scattering. Another interesting thing is that forward scattering increases with resist thickness. So if you're going to do a lift up, like Mark will talk about later on, it's actually in your advantage to have a fairly large resist thickness, because you can see that as the beam forward scatters, you'll actually generate sort of an undercut pattern, which is something that you want for doing liftoff. It makes it a lot easier. And now I'm going to show you how the proximity effect correction is done. So let's say that you have this pattern, you want to expose a grating, you want to, and with a long line, in the center. And then you're going to, again, convolve with the point spread function to see how the energy is deposited. You can see that there's very little energy being deposited here and on the edges, and as well as the corners. So if you normalize the energy that you're depositing as 1, then let's say that you have arranged your resist process so that it will clear at a dose of 0.5. And in that case, the pattern that you would get after developing is given by these contours here, but these blue contours. So you would see that the single line has disappeared, and the corners and the edges also have suffered from the proximity effect. So if you put your pattern through the proximity effect correction program, which in our case here at Nano is called Beamer, what the program will do is that it will calculate the error between what you saw in the previous slide and what you want, and it will increase the doses of the pattern such that you get a uniform dose, and your pattern fidelity will be good. So you can see that here in the single line, the doses are increasing. The blue doses are lowest doses, and the red doses are the highest doses. So you can see how the dose keeps increasing for the line. Similarly, at the corners and on the edges of this grating, you have increased dose. And then once you convolve this and develop it, then you see that you can get something that's pretty close to what you designed. And lastly, let me show you some patterns where you have a large grating that's been exposed without doing proximity effect correction. And at the center, you can see that you have pretty good grating lines. At the edges, you can see that the lines are getting slightly thinner, but at the corner, they're really too thin. So the change in line width is pretty obvious. Whereas if you run it through the proximity effect correction program before, you can see that all 3 instances that we're showing here are pretty much the same. So you'll get very good fidelity if you use a proximity effect correction program on all your patterns before you expose them. You will pretty much always get what you want. And if you choose your doses carefully, you might not even have to do a dose matrix. So now I'm going to hand over to Mark to continue the presentation.
So that was a great explanation of proximity effect correction, and is why I have that slide that says e-beam lithography is not a copying machine, because it's not. There's so many things that need to go into it. E-beam lithography is not also have infinite resolution, let's put it. Our beam size, we can get down to 1 nanometer. I've even seen work done in transmission electron microscopes with our beam can get down to about 2 nanometers. I've even seen transmission electron microscopes used for lithography with 1 nanometer and less beams, but you don't get features that size. There's a bunch of reasons for that. One of them is throughput. Well, if we're going to write with 100 picoamps, it's going to take a really long time to write compared to writing with 100 nanoamps, like 1,000 times probably. The beam gets bigger as you put more current down it. With e-beam lithography design columns, that beam current won't change the size of the beam as much. With SEMs, it blows up really quickly. We've just talked about forward scatter and back scatter, but there's also the pixel size and the placement that can have a lot to do with how good your resolution, your fidelity is. We need to focus and stigmate. That focus and stigmation needs to be the same everywhere on your pattern and on your substrate. But really, it's pattern transfer process with less granularity and a resist contrast that have a lot to do with it. So in the first thing, in terms of beam current and beam size, we have this plot here of the Eleonics nominal beam current at one of the aperture sizes, which goes from about 10 nanoamps up to about 100 nanoamps. We get this curve. We're looking at the beam diameter in a linear scale against beam diameter in a log scale against beam current in a log scale. And then if you look at the slope here, the slope of this is very similar to the slope of this. This is the red, this is the smaller aperture, and we can go from like 100 picoamps on this to 10 nanoamps. So for a range from like here at this inflection point up to like maybe here, basically from about 2 nanoamps up to about 50 nanoamps or so, it turns out on our tool anyway, but some other tools it's similar, that the beam diameter in nanometers is equal to the beam current in nanoamps. So this is looking at the same sort of point spread function, but from a different viewpoint, i.e., if we want to have high resolution and we have thin resist like this, like 20 nanometers of PMMA, then we'll get a fairly small spot size. On the other hand, if we have 400 nanometers of PMMA, and this is all being done at 10 kilovolts, then we're going to get a huge spot size, like 300 nanometers instead of 20. I use these lower voltages because they illustrate the point more dramatically. And typically, if you're using a reasonable resist range, it's like less than, I don't know, 400 nanometers or something. Even at 50 kV, your forward scatter is going to be minimal for most patterns. So if we're at 125 kV, even in 400 nanometers of PMMA, we still get a 50 nanometer spot. But if we tried to do that same thing at 10 kV, we're going to get this 400 nanometer spot. And we can pick our different pixel step sizes. I talked about this a little bit before. So if we wanted to use a 2 nanometer beam over here with a 10 nanometer pixel step size, which is kind of the default thing, you might think that's reasonable. But in fact, we very sparsely fill this pattern. We're going to get a lot of line edge roughness. And we're probably not going to get a very continuous dose across here, which is probably not that important. It's going to be slow. It's not going to really be round. On the other hand, if we pick our pixel size and our beam diameter size to be equal, that may work very well for us as the common default to start with. On the other hand, maybe we want to go really fast and we know a little bit more about what we're doing, and we say, let's go with a beam size that's twice our pixel size. We intentionally round off some of these corners. We make our feature more circular, and we go fast all at the same time. Or in a kind of naive way, you could say, I'm going to use the smallest beam diameter I can, which is going to mean small beam current, and I'm going to use a tiny pixel size, and I wanted to find a 100 nanometer circle. We could do this. It's going to be round, although maybe we're going to see a little line edge roughness here, but it's going to be slow. If we increase our beam size, but maintain the pixel size, now we get this nice overlap. Now we get this nice overlap here. We probably round things up and we get higher throughput. Or we could say, man, we're going to do 20 nanometer beams. We're going to use huge beam current, and we're going to do this with tiny little step sizes. Now, the two problems here. One is, one is that our feature is going to grow. You can see this here. We could fix that by biasing everything down and making it a bit smaller. But we're probably not going to have a clock speed that will allow us to give the dose we want, because we've got so much current in the beam and such a little pixel. We can't drive the beam from pixel to pixel fast enough to not overexpose. So moving on to the next thing, we have problems with focus and stigmation. When we're going straight down the column with undeflected beam, we get beautiful focus and stigmation. That's how we focus and stigmate. But as we move off to the side, the bigger the field we have, the path length is longer, our focus changes, and our stig will change so that our spot sizes will no longer be this beautiful round gray thing we have here. but these beige ellipsoidal stuff. So that's what I was talking about before when we were talking about subfields, that will load new subfield, will load new focus estimation data for each subfield. So as we go farther away from the center, we have good control of the beam. So this is just me repeating in text what I just said. We also need to have good focus. So how do we have good focus? By knowing the distance from the substrate to the final lens. And the way we can do that is by having a laser that bounces off our substrate onto a linear detector. And that point at which it hits that linear detector tells us the distance. And therefore, we can change the focus. There are two ways of changing focus. One way that's used in most tools is we change the current through the final lens, and that changes the focal distance of the lens. Or we can actually physically move the stage up and down. On the Eleonics tools, that's what happens. This is very nice in some ways because we get rid of E cross B and some rotational effects that you might get by changing the flux in the final lens. The downside is the stage takes a second to 2 seconds or 3 or 4 seconds even to move up and down, whereas we can change the flux to the final lens much more quickly. Yeah. There also could be substrate issues. Semiconductor wafers are just beautifully flat and smooth, right? Well, they actually, and they're parallel. They're smooth, but they're not really flat in that they'll often have a spherical distortion. So like a 4-inch wafer might be 40 microns higher in the center than at the edges unless you have some good clamping system. But I point this out because if somebody brings in a glass slide or maybe a piece of tungsten that they've had machined, it will not be smooth, it will not be flat, it will not be parallel, and these will all be issues. If we have non-conductive substrates like silicon nitride or something, that's a problem because it's an electron, it's not a photon. That electron wants to go where the field lines are, not in a straight line like a photon does. So as we charge up the substrate, we'll lose focus. The same thing can happen depending on your voltage and your insulating layers. Many people will have 285 nanometers of silicon oxide on it. They're working with graphene. If we work at 5 kV, some of those electrons are going to get stuck in that oxide. If we work at 100 kV, virtually all those electrons are going to go through the oxide into the substrate, get carried away to ground. We can fix that by putting a conductive film on top of our substrate and then grounding that conductive film so as the electron comes down, it just sees ground potential, it doesn't get deflected. You can have various other issues. One of the ones that is more important for Wraith, EBBC types tools or Joel tools is that the substrate is rotated with respect to the stage movement. Those tools aren't able to accommodate that so well, so it won't be able to line up and write the way we'd like to. I put this in here because if people email me after the talk, I will send this talk back out again. I think it's a generally useful reference of approximately the different sensitivities for a classic 950 kPa developed at room temperature. This is important for about 90 seconds with 3:1 IPA MIBK for sort of semi-dense features that are bigger than 1/4 of a micron. You know, these are approximately good values to start with. So what we'd like to have are resist with really good contrast. And the reason we want resist with really good contrast is we either want resist or we don't want resist. We don't want some sloping resist typically. So this is a plot that tries to show that. And the idea here is we have a representation of our Gaussian beam. And then we have this line here of the dose to clear. So this is the absorbed energy in the substrate versus distance. So at what we'd like to have is this to be a very fine line, and either it exposes the resist and it's all gone when we develop, or it doesn't expose the resist and it all stays. Now that doesn't happen exactly, but we'd like to get as close as we can. One of the ways that it doesn't happen is something like this. If we have a low contrast process, that is, there's a range over which the dose will be enough to let some of the resist get developed away. And it's a terrible graphic. I was doing it yesterday, and anyway, hopefully I can make a better one. The idea here is within this range, we've got different amounts of dose, and then the resist itself gets developed away more or less. And now we got sloping sidewalls. Sloping sidewalls are terrible when we try to transfer our process into a substrate. Now, a way that we can improve contrast is by doing cold development, at least for positive resist. This is not going to work well for negative resist, but positive resist, where the area of the resist that you expose is the area that gets washed away. And this is beautiful work that was done by a student of Hank's in NSL 10 years ago now. If we develop at 50 I can't see because my thing is in the way, but I think this is 15 degrees C up here. 15. We get 15 nanometer lines, and these are images of silicon oxide that's been etched after the resist has been exposed and developed. If we go to 0 degrees C, we get these 10 nanometer lines. At minus 15, we get these even finer lines. And then if you go to minus 30, it's terrible. And the reason for that is this. This is a very complicated plot. I suggest you look at it later and study it more if you're really interested. What he's showing here is this aquamarine line here in the middle corresponds to minus 15, and that's optimal. It's optimal because this thing is as close to vertical as any of the lines in this chart are. And it turns out as you have to give it higher and higher dose, you get to a point where the chains in the polymer, instead of getting broken up and getting washed away, they cross-link to each other and you start getting negative resist. But that's probably not what I should bring up in this talk. The same thing will work for O-xylene and ZEP for developer. And interestingly, not only do you get increased contrast, or because you get increased contrast, maybe, if I make 40 nanometer lines in ZEP and develop it at room temperature, I get this ragged stuff here, these not very nice lines. If I do the same thing at 0 degrees C with a higher dose, I get beautiful, nice, sharp edges here. And this is what we prefer to see. We're getting a little bit short on time if people want to ask questions, but I still really want to show this. This is some work that Juan did with Hank Smith at a startup company of his when we first started evaluating CSAR resist, which is similar to ZEP. And there are these beautiful cross sections. And what I want to point out is this stuff was done at 30 kV, and you get some undercut. 30 kV is really great in some ways because you get undercut if you're doing liftoff, that's helpful. And if you do more, it starts to really get undercut and you get very little holding the line in place, or maybe you get this. I point this out because Juan did these beautiful cross sections and you can see what's happening. If we looked at an aerial view of the same thing, we might not see a huge amount of difference. We'd see the line width changing and the gap changing, but we wouldn't realize that lines were starting to fall over because of this. So if you get the dose dead on, then you get something like this, and you get this beautiful, nice rectilinear cross section of the lines. And this is all done at 30 kV. I then expose some of this stuff at 125 kV, and now we get a 13:1 aspect ratio. And you can see a little bit of undercut in this fine line here, but by and large, you get very little undercut, beautiful rectilinear stuff. And that's working at an even thicker resist, 520 nanometers, instead of the previous, I think it was 300 nanometers, but at a much higher voltage. The stuff up here is supposed to represent an aerial view of the images we're exposing here. So we have positive resist like PMA and ZEP CSAR. They're both long chain polymers. PMA is much less sensitive. ZEP is much more sensitive, i.e. you can write faster. It also has a good etch resistance, but it's got a short shelf life. It's a little hassle to work with and it costs a lot more. They're negative resist like HSQ and MAN. Those are the only two that are really reasonable to work with. SU8 is so high sensitivity, it's very hard to work with. HSQ is a wonderful, beautifully high resolution, probably the highest resolution resist, but it turns into silicon oxide, so you have to strip with hydrofluoric. MAN, on the other hand, you can strip with organic solvents, but it's a little harder to work with, and its resolution is probably around 50 nanometers, and that's if you're doing a really good job. So I'm going to briefly finish up with some pattern transfer, and then if anybody has any questions, we'd love to talk to people. So liftoff, this is liftoff. Expose resist, develop it, deposit material with an E-beam evaporator typically, and then you solvate this stuff, that resist goes away and you're left with these metal patterns. That's good. This is bad when you've got resist with rounded edges and a bad E-beam evaporator. You can't lift this off. The metal protects the resist from getting solvated. There are limits to E-beam evaporation though, and that is that you typically can't lift off any more than half of your resist thickness, and that's because as you evaporate, This red stuff gets bigger and bigger, and it accumulates at the edges, and it makes these little mushroom caps until you get something like this. And that's typically going to happen with about half when you try to get more metal in your slots than you have room for. This is a nice example of that in practice, that we have all this metal deposited up here. It gets really big, it pinches off the holes where it was supposed to come through. So instead of getting rectangles down here like you wanted, you're getting these pyramidal shapes. We can also do RIE. I include this very briefly just to show that one of the issues with RIE, we've got HSQ here, where's my cursor, in the top, and that's the etch mask. You can see how this gets rounded with time. And that's got to do with kerning, with molecules impacting and sputtering rather than RIE, but that's another talk. If you really want to get high aspect ratios, think about doing electroplating. I've been told that MIT.nano, Kurt runs some electroplating stuff. And with electroplating, if you can make a form, then you should be able to electroplate up your gold to really high aspect ratios. I showed you pictures before with 13:1 aspect ratios. I've certainly seen 20:1, and some people can do 100:1 aspect ratios with electroplating. So that's my talk, and Juan's. So if anybody has any questions, you can unmute yourself and do the chat thing, because now I can look at chat. Oh, it says we stopped recording at some point. I don't know if that's true or not. So does anybody have any questions in chat or otherwise?
I have a question.
Yeah?
How large an area could you process realistically? Could you do centimeters squared? How big an area could you do?
Sure. So the question is, how big an area can you do? So if you use the HS50, which is a 50 keV acceleration voltage, therefore our 300 plus and minus volts deflection allow it to deflect about 500 microns off center, you get 1 millimeter field. So if you want to do a centimeter square, that means it's going to take you 100 fields. Well, this is perfectly doable, but it depends on what you're writing in those fields, right? So if you're writing very sparse patterns, then each field might take you 5 seconds to write, let's say. So that's 500 seconds. So that's less than 10 minutes, and that's great. On the other hand, if you have, let's say, dense 100 nanometer lines and spaces, each field might take you 5 minutes to write, and that's 500 minutes, and that's a lot more time.
So for things like metasurfaces elements, the sub-wavelength features, I think
Sorry, you're not very loud. Can you try that again and just be a little bit louder?
Yes, I was saying for metasurfaces elements, so those are sub-wavelength features. Would that be considered a dense array of features?
Yeah, so it's not the size so much as the percentage of the area covered is our first order thing when we're going to calculate throughput, i.e. how many electrons in total do I need to put down? Yeah. In addition to that, the next thing that's going to typically impact throughput is how many primitive shapes do I have? So if you're trying to write a lot of circles that have been decomposed into little tiny shapes, you may have tens of millions of shapes. And the tool now, as I understand it, as best I can back calculate it, waits 5 microseconds before each primitive. So if you've got tens of millions of primitives, you're going to have a big impact on throughput. On the other hand, if you want to write a grading that's 100 nanometer lines and spaces, yeah, that's not so many things to write, because each grading line will be just one rectangle.
Okay, thank you. Appreciate it.
Sure. And feel free to email me or whatever if you want to talk about this some more.
I have a question on the alignment. So what is the tolerance like? How close can you get for the minimum alignment?
Sure. So I thought about putting specs of tools in, but I think they're semi-misleading because it has to do with real world considerations. So the nominal spec for the alignment on both of our tools, I think, is 25 nanometers plus and minus 2 sigma. In point of fact, if you have really terrible lines to align to, or your alignment marks are really far away from what you're trying to get overlaid, that's going to impact. And what I mean by this is I didn't talk anything at all about the imaging system. We have both backscatter imaging and secondary electron imaging. So if you have something like a 50 nanometer thick gold line with nice sharp edges that's underneath 200 nanometers of PMMA, you'll get a beautiful secondary electron signal from that that will have nice sharp edges, like the contrast I was trying to point out before, that allows you to locate the center of that line very accurately. On the other hand, if you have, say, a 1 micron wide line etched 1 micron deep into a substrate without nice sharp edges with a micron of resist on top of it, you won't know what the center of your line is very well, and that will add to the error budget.
I see. And if you want a gold-free process, what other metals would you recommend for the alignment marks?
Oh, a gold-free process? Well, platinum
Yeah.
works very well. I mean, for secondary electron emission, you're really mostly thinking about molecular cross-section, right? So heavier metals are going to do better. So, you know, tungsten works reasonably well. Platinum works well. Nickel can work. Aluminum, not so much. You know, it's right next to silicon, right?
Mm-hmm.
Hard to get contrast. On the other hand, we do have backscatter electron detectors that will allow you to do some heavy metals underneath very thick resist that still will allow you to get good imaging and therefore alignment.
I see. Thank you.
Sure. Anyone else?
I just have a quick logistics question.
Yeah.
In terms of usage, training wise, what's the length of training someone to be able to actually make patterns? Or does it
Sure.
depend on whether the person has a background in SEM and TEM? And then what is the is it possible to have the MIT staff do patterning for us?
Yeah, so in general, I don't do fee for service. Occasionally, I've done 1 or 2 testings in special circumstances. We really want to do pedagogy, that is teaching people how to do things. So typically, we want people to come in and do their own work. So here are some of the questions I ask new users. Have you done SEM before? Because if you're trying to make high resolution patterns, you're going to want to be able to use an SEM to image the patterns you made. Are you a qualified MIT.nano user? Have you done the chemical hazardous waste training? Have you done all the other trainings that need to be done? Do you know what resist you're going to use? Have somebody else done a process like this before? Or maybe it's a simple process that I can help you with, you know, because I'll know a priori kind of parameters you might want to use. So that's the back part of it, right? The part specific to the e-beam lithography is I typically, or Juan typically trains people for 2 to 2.5 hours on 2 different sessions to get you up to speed to do basic writing. If you want to do alignment, I usually do another 2-hour, 2.5 hour session to teach alignment. You know, people are good at SEM and other things. Maybe it's going to take an hour and a half. It depends on how long your pattern is to write. And then after that, you can use the tool on your own. So it depends a lot on how complicated the thing is that you want to do. You know, if you want to write let's make it more reasonable. If you want to write 300 nanometer lines and spaces on silicon in PMMA for liftoff of 50 nanometers of gold, you know, yeah, the second time you write, you probably get something pretty close to that with a dose matrix. And the third time you write, you should be able to write that kind of stuff with a dose matrix and get it to work. Assuming you know how to run the e-beam evaporator and use the solvent bench to do your liftoff and the solvent bench to do your development.
Okay, thank you.
Sure. So I still have time if anybody else is interested in chatting. So I'm going to take that as nobody else is interested. And my phone will turn on. And good, we're ending 5 minutes early nominally. If anybody wants to contact me, if you contact me, I will send out the slide deck to you. The recording will be available later. I'm going to leave it at that. Thanks very much.
Thank you.